Well, shall I just start, Ross? Do you want to say something, or shall I just go for it? Okay, I'm just going to get going, I think. All right, everyone. Yeah, so I'm going to present some work with Malta, who a lot of you know, and I'd like to acknowledge in particular the Humboldt Foundation for their support. Now, I'm going to be considering just a classic 2D wave scattering problem. It's either an acoustics problem or a water waves problem, in which we've got a straight line array of n identical, equally spaced circular cylinders within some acoustic medium, which I'm showing you at the bottom of the slide here. I'm going to excite motions by a plane ambient wave traveling at some angle psi. It's just the standard stuff here. And with some wave number k, which you can associate to a frequency of motion in the usual way, and I'll just refer to as a frequency from now on. I'm also going to include all of the usual assumptions of linear wave theory, including time harmonic motions. And so that leaves us with something very familiar. It's the 2D Helmholtz equation, which is exterior to the cylinders. And then we've got Neumann boundary conditions on the cylinders, and plus some radiation conditions at infinity, of course, which I'm not showing on the schematic here. And I'm going to non-dimensionalize, so there's just a unit distance between adjacent cylinders. And so we just have four parameters in this problem. We've got the frequency k, the angle psi, the number of cylinders n, and the cylinder radius a. Now I'm going to relate the solutions of that problem to what are known as Rayleigh Bloch waves. So Rayleigh Bloch waves are unforced solutions along a corresponding infinite array. Then they propagate along the array in either direction from symmetry with some wave number beta, and that wave number is strictly greater than k, and then they decay exponentially away from the array. So what we're talking about here is a class of array-bound wave. So now, with a very, very brief introduction, it's easy to not understand how amazing Rayleigh Bloch waves are. So I just want to give you a couple of things to help you understand why they're worth looking at. So first, there's no one medium that is supporting the Rayleigh Bloch waves. They are existing because of the multiple scattering of waves between cylinders. And they're traveling along a one-dimensional space which is lower than the two-dimensional space which we're considering overall. So that means that the scattered waves are interfering in a very special way. That means the energy isn't leaking away from the array, which is what would happen in general. And they exist for all frequencies up to some cutoff, which I'm calling KC, depends on the radius A, and it's strictly less than pi. Now, this talk is all about what happens above that cutoff. Another reason, well, primary reason actually that we're interested in Rayleigh Bloch waves is that they're going to help us understand the resonant properties on finite arrays. So what I'm showing you on this slide are the wave loads on the middle cylinder in a finite array versus frequency. I'm showing you results for two different array lengths on the two different rows, and then three different cylinder radii along the columns. And for reference, there are the corresponding results for just single cylinders. The results are shown as resonances when k is just below a multiple of pi. what I want you to note here is that the number of resonances doesn't depend on the array length. So you can see that if you compare the different rows, but it does depend on the radius of the cylinders. So compare the different columns. And as you increase the radius, you lose resonances. But you always have the primary resonance just below k is equal to pi. And there's a lot that is known about those resonances. So that work was kind of active 10 to 20 years ago. And the culmination of it was that Rayleigh Bloch waves create those primary resonances. So there are three parts to this process. First is that the ambient wave has to excite a Rayleigh Bloch wave. Then second, the Rayleigh Bloch wave has to excite a reflected Rayleigh Bloch wave when it interacts with an array end. And then third, we have to have coherence of the reflected and re-reflected Rayleigh Bloch waves. So what I've just described to you there is in many respects quite similar to just a standard resonance condition, but it's in a much more complicated setting. And what's been shown is that the three conditions are achieved just below the cutoff, and they create symmetric low profiles like the ones that I'm showing you at the bottom of the slide here. So then the question is, what is the source of the resonances above the cutoff? And in order to be able to give you some idea of what's going on there, I'm going to need to know what happens to the Rayleigh Bloch waves when we go above the cutoff. So in order to be able to do this, we're going to have to be able to deal with complex valued wave numbers beta. And that means that we can't just use standard solution methods that probably a lot of you are very familiar with. So I'm going to introduce the method that we use, which is a non-standard one, and it's not the focus of this talk, so I've just condensed it into a single slide. What I want to do is just convey enough of the solution method that you're able to understand the results on subsequent slides. So what we've done is we've just isolated a single cylinder in what I'm calling a generalized channel. It's got a unit width for the space in between the cylinders. And then I'm decomposing the wave fields on both sides of the channel into the rightward and leftward traveling components of the wave field, and just expressing those as integrals, where the integration contours gamma. They also have complex branches, which means that we're also considering decaying waves. And then the crucial part is that we derive the reflection transmission operators, which I'm calling KR and T, and they relate the amplitude functions A and B that you can see in the integrands at the top. And we then use those reflection transmission operators to define a transfer operator, which I'm calling P, and that maps the amplitude functions on the left of the channel to the right of the channel. And just notice that the transfer operator depends only on the frequency K and the radius A. Okay, so you now find the Rayleigh Bloch waves from the spectrum of the transfer operator. And what I'm showing you here is a typical example below the cutoff. On the left, what you're seeing are the eigenvalues in the complex plane, and I've highlighted one eigenvalue in particular. It's xi beta. So that defines the Rayleigh Bloch wave. And then note that there's also, from symmetry, an eigenvalue x minus I beta. So that's just the Rayleigh Bloch wave traveling the opposite direction along the array. And those two eigenvalues together gives the discrete spectrum of the operator. Then we have this set of closest spaced eigenvalues around the unit circle and on the positive real axis. And they are a numerical approximation of the continuous spectrum So that continuous spectrum defines forced solutions, ones with an ambient wave. On the right, you're seeing the eigenfunction for the Rayleigh Bloch wave in the upper half of the complex plane, the one that I'm highlighting on the left. So the eigenfunction defines the amplitude functions A and B that go into the Rayleigh Bloch wave. Then those grey regions are the decaying part of the spectrum, and the white is the propagating. And also here, just note that we've got a large peak in the blue curve, and that's just telling us that the Rayleigh Bloch wave is propagating rightwards along the array. Okay, now this is where we had a bit of a technical issue that we worked out earlier. I'm showing you a short movie of the spectrum evolving with increasing frequency up to the first cutoff and then just beyond it. I want to say a few words before I show this to you, but I'll try to just tell you the key points to look out for as it's playing on loop. What you're seeing here is that the Rayleigh Bloch eigenvalues are chasing around the unit circle as frequency increases, and they're getting increasingly far away from the tips of the continuous spectrum, although the continuous spectrum is chasing behind the Rayleigh Bloch eigenvalues. And if you look on the right-hand side, and you see that as frequency increases, the blue and magenta curves, they are tending towards each other, and that's telling us that the Rayleigh Bloch waves are becoming a standing wave. Then there's this point where the eigenvalues meet -1, at which point they jump onto the real axis. One goes inside the unit circle, one outside the unit circle. And that's telling us that the Rayleigh Bloch wave number beta is going from real to complex valued. And that means that we're transitioning from propagating to decaying. And that is my way of looking at defining the cutoff. Okay, now just watch something interesting is happening now. What I've done is I've restarted the movie just above the cutoff. I hope you saw that another pair of eigenvalues appeared very quickly at the beginning there. They interacted with the existing ones, and then they start chasing around the inside and outside of the unit circle in the upper and lower halves of the complex plane. Also note that in the eigenfunction, we get these delta function type features appearing. So what we have here is that above the cutoff, we have an interval where there are 4 eigenvalues in the discrete spectrum rather than 2. Also notice as k gets towards 2 pi, the eigenvalues start to get in the discrete spectrum, get close to the continuous spectrum, and I have to give up tracking the discrete spectrum. So you just saw it then. Okay, so that's a big problem. I can't track the discrete spectrum anymore when it gets too close to the continuous spectrum, because I don't know what's happening around k is equal to 2 pi, and that's really one of the most interesting points, because that's where the resonance is going to occur. So I was stuck until I had my own very small eureka moment, which was to modify the boundary condition on the cylinder to introduce some artificial damping with damping parameter lambda. So what the damping does is it pushes half of the discrete spectrum away from the unit circle, and away from the continuous spectrum. It doesn't affect the continuous spectrum though, because that's dictated by the quasi-periodicity that's given by the ambient wave component. Right, on the left-hand side, you see that for a positive value of lambda, I'm pushing the discrete spectrum in one direction, and then on the right-hand side, the negative value, I'm pushing in the opposite direction. So I can now track the discrete spectrum through the second cutoff by choosing values of lambda, and then I recover the undamped case by just decreasing lambda to 0 in small steps and tracking the discrete spectrum. And I'm trying on this slide to illustrate that process and the method, and also what you find for the discrete spectrum. So the different colors are different frequencies, and the arrows are the direction of evolution towards the undamped problem. The maroon is just below k is equal to 2 pi, and the eigenvalues are very close to the unit circle. Then the green is at what I'll call the second cutoff, and there all of the eigenvalues, they coalesce at 1. And then the blue is just above that second cutoff, and the eigenvalues are moved onto the positive and real axis. So what we found here looks like embedding. It's a very special form of embedding because it's into the continuous spectrum, which defines decaying ambient waves. Okay, so now remember that for a radius of 0.25, there are only 2 resonances. And if we look at the eigenvalues of the transfer operator above the second cutoff, we find no evidence of a discrete spectrum. That's what I'm showing you with the movie on the right. I can add as much damping as I like, but still no discrete spectrum appears. So what we've got is consistency between what looks like a complete cutoff of the discrete spectrum and an absence of resonance. For the small radius case, 0.15, we do have a third resonance. Okay, so again, look on the right, and I've got a large damping parameter, 0.5, so you can clearly see what's going on, the discrete spectrum in particular. So, but remember, that just means you're seeing half of the discrete spectrum. So now we're getting up to that second cutoff, and what you'll see is a bit like what we saw last time. It looks like the discrete spectrum disappears, but then if we just keep pushing the frequency to higher values, very soon it's going to come. The discrete spectrum seems to reappear. Okay, so again, there's a consistency between the existence of Rayleigh Bloch waves and the resonances. Just one more thing to show you. The large resonance case. Okay, there's only 1 resonance here. So again, look at what's going on. The eigenvalues on the right-hand side. There's something very different that happens above the first cutoff. Initially, it's behaving as we saw before, but then it's going to reverse its behavior. And we're going to get one of the eigenvalues going into the continuous spectrum on the unit circle, and the other one going towards unit spectrum at the origin. Okay, so it seems like everything's holding together at this point, but if we keep on pushing to higher frequencies, then you're going to see the discrete spectrum reappears again. So this breaks that simple relationship between the existence of Rayleigh Bloch waves and the resonances. Well, it actually turns out that in this case, you don't get a third resonance, even though you've got Rayleigh Bloch waves, because you don't get enough reflection of Rayleigh Bloch waves at the array ends. Okay, so look, I realize I've gone a bit over time. There are my conclusions. I'll leave the minute or so that I've got for any questions.
Any questions from the audience?
Look, I have a question. Whether these resonances are related somehow with the so-called phonoresonance?
Oh, yeah, I